This video is about visualizing ideas in group theory. If you've never met group theory before, don't worry, this video can serve as an introduction. A group such as D4 is a set of elements and a way to combine them through a multiplication operation, denoted here by this dot. For example, in D4, r dot s is SR cubed. The group elements and the way they multiply must follow a set of rules, known as the group axioms. This is the multiplication table for D4. Note the operation is not necessarily commutative. What this means is that unlike addition where 2 plus 3 equals 3 plus 2, and multiplication where 2 times 3 equals 3 times 2, notice here that SR is different to R dot S. So when we have a set of elements, a way to multiply them, and these elements and their multiplication follow the group axioms, we have a group. To make things more concrete than abstract elements like E's, S's and R's, we'll think of the group elements as representing symmetry operations. So, what is a symmetry operation? This is the Symmetron. With its huge processing power and laser-precise grabbers, it can do anything imaginable to what you feed it. But it does come with one simple flaw. If its output doesn't look exactly like its input, it explodes. The actions the Symmetron is allowed to perform are called symmetry operations. So what could the Symmetron do to a square, for example? Well, it could rotate it 90 degrees clockwise, or it could flip it along its vertical axis. In other words, 90-degree rotations and vertical flips are both symmetry actions of the square. What else could the Symmetron do? Well, it could combine the two symmetry operations into a new one. It does this simply by performing them one after the other. This is the idea behind a group axiom called closure. Combine two symmetries of some object, and you get another symmetry. A rotation followed by a flip along the vertical is the same as a flip along the diagonal. We could get into philosophical details, but to understand why, keep track of the corners. What else can the Symmetron do? What I'm asking is, what else could we do to a square without changing its appearance? Although simple, it's easy to forget the Symmetron could just do nothing. In fact, no matter how complicated the object you feed the Symmetron, you can always avoid an explosion by setting the dial to do nothing. This is another group axiom. A group always has what we call an identity element. We usually call this element E. To put this into our context of symmetries, do nothing is always a symmetry. Next, notice the opposite to any symmetry operation is again a symmetry operation. This is the idea behind our third group axiom. Every element in a group has its opposite, or its inverse. The inverse is about undoing an action, so that combining a symmetry operation with its inverse yields the identity, or do nothing. The final group axiom is associativity. This one's a bit more complicated. In a nutshell, it allows us to string together multiple group operations like this, without specifying which happens first with brackets. How come? Well, it doesn't matter where the brackets go. Take a look at this example. Work out the brackets first and both yield the same result. So that's associativity, our final group axiom. Great! So now we have a good idea of what a group is and how its structure relates to symmetry. Take a look at some of the symmetry operations groups can represent. Permutation symmetry, symmetries of a polygon, rotational symmetry. Often, we even find groups within groups. We call these subgroups. Let's bring back D4. D4 contains a group C4. C4 can model the rotational symmetries of a square. It is also the full symmetry group of a cyclically symmetric object like this one. C4 isn't just any subgroup of D4. Take a look at this. We colour elements that belong to the subgroup in red and all the others in blue. Notice anything? There's a general rule here. Anything red times anything red is red. Red times blue or blue times red is blue, and blue times blue is red. So you could be specific and say something like S times R is SR, or more general, something blue times something red is blue. We've actually drawn another group here. This is C2, the symmetry group for objects with twofold rotational symmetry. So when you look less closely at D4, it behaves a lot like C2. This is the idea behind quotient groups. We can summarize everything in the following equation. We started with a group, D4, found another group within the group, C4, and by grouping elements according to C4, we obtained a quotient group, C2. So there you have it. We hope the Symmetron could bring the group axioms to life. We're big fans of mathematical visualization. We'd love to read your comments on how you picture these concepts yourself. Until then, this has been Blue Hydrant. See you next time.